When we talk about block storage in AWS, we're referring to a storage model that works very much like a traditional hard drive attached to a computer. Data is stored in fixed-size blocks, and the operating system sees this storage as a raw disk that it can format, mount, and use for low-level operations. This is very different from object storage, where data is accessed through APIs rather than mounted as a drive. In AWS, the primary block storage service you need to understand is Amazon Elastic Block Store, or Amazon EBS. Amazon EBS provides persistent block storage volumes that you attach to Amazon EC2 instances. Once attached, an EBS volume behaves like a physical disk drive. You can install an operating system on it, store application files, or run databases that require consistent performance and low latency. One of the most important characteristics of Amazon EBS is persistence. Data stored on an EBS volume exists independently of the EC2 instance. If an EC2 instance is stopped or terminated, the data on the EBS volume remains intact unless you explicitly configure the volume to be deleted. This makes EBS ideal for workloads where data durability is critical, such as databases and application state. Another key characteristic is that EBS volumes are scoped to a single availability zone. Each volume is automatically replicated within that availability zone to protect against hardware failure, but it cannot be directly attached to an instance in another OS. If you need the data in a different availability zone, you create a snapshot of the volume and restore it there. This OS-level design is a common exam point. Security is also built into EBS. Volumes support encryption at rest and encryption in transit using AWS Key Management Service, which is especially important for compliance-sensitive workloads. In addition, EBS snapshots are stored durably in Amazon S3 and are incremental, meaning only the blocks that change are saved after the first snapshot, which reduces storage costs. Now let's talk about the types of Amazon EBS volumes, because this is a frequent exam topic. EBS volumes are divided into SSD-backed and HDD-backed options, depending on whether the workload prioritizes low latency or high throughput. For SSD-backed volumes, the most common option is GP3, or General Purpose SSD. This is the default choice for most workloads. It offers a balance between price and performance and is suitable for boot volumes, application servers, and small to medium databases. One important feature of GP3 is that you can scale performance independently of storage size, which gives you flexibility and cost control. For more demanding workloads, there is IO2, or Provision IOPS SSD. This volume type is designed for mission-critical systems that require very high and consistent IOPS with extremely low latency. Typical use cases include large relational databases and high-performance NoSQL databases where performance consistency is essential. On the HDD backside, EBS offers volumes optimized for throughput rather than IOPSes. The SA1 volume, or throughput-optimized HDD, is ideal for large, sequential workloads such as big data processing, log analysis, and data warehouses. It provides high throughput at a lower cost than SSD volumes. Finally, SC1, or cold HDD, is the lowest cost EBS option. It's intended for infrequently accessed data where performance is not critical, but storage cost is. This might include large datasets that are rarely read but still need to remain available on block storage. To summarize for the exam, you should think of Amazon EBS whenever a question mentions operating systems, boot volumes, mounted disks, databases, or low-latency storage attached to EC2. If the workload needs a disk that the OS can mount and manage directly, EBS is the correct choice. If instead the question mentions APIs, buckets, or objects, then Amazon's 3, not EBS, is the correct service. When we talk about file storage in AWS, we're talking about storage that behaves like a traditional file system, the kind most people are familiar with from on-premises environments. File storage allows multiple systems to access the same files at the same time, using standard file paths, directories, and file permissions. This makes it ideal for shared data, collaborative workloads, and applications that expect a mounted file system rather than API-based access. In AWS, the two main file storage solutions you need to understand for the Cloud Practitioner exam are Amazon Elastic File System, Amazon EFS, and the Amazon FSx family. Let's start with Amazon EFS. Amazon EFS is a fully managed, serverless file storage service designed primarily for Linux workloads. You can think of EFS as a shared network file system that multiple EC2 instances can mount and access simultaneously. Unlike block storage, which is attached to a single instance, EFS is built specifically for shared access. One of the biggest advantages of EFS is elasticity. You don't need to provision storage size in advance. The file system automatically grows and shrinks as you add or remove files. This makes it very easy to operate and removes the need for capacity planning. From an availability perspective, EFS stores data redundantly across multiple availability zones, so it is highly available and durable by default. EFS uses the NFS protocol, specifically NFS v4, which makes it a natural fit for Linux-based applications. Common use cases include shared storage for web servers, content management systems, development and testing environments, and analytics workloads where multiple instances need access to the same data. For cost optimization, EFS also supports lifecycle management, allowing infrequently accessed files to be moved to a lower-cost tier automatically. Now let's talk about the Amazon FSx family, which is designed for more specialized or enterprise-grade file system needs. Amazon FSx provides fully managed file systems that are compatible with well-known industry-standard file systems. This is especially important when organizations are migrating existing applications that depend on specific file system features. Amazon FSx for Windows. File Server provides a native Windows file system using the SMB protocol. It integrates directly with Microsoft Active Directory and is ideal for traditional Windows workloads, such as shared file servers, .NET applications, and SQL Server environments that expect SMB-based storage. Amazon FSx for Lustre is optimized for high-performance computing workloads. It's designed to deliver extremely high throughput and low latency, making it ideal for use cases like machine learning, media rendering, scientific simulations, and big data processing. A key exam point is that FSx for Lustre integrates seamlessly with Amazon S3, allowing you to process large datasets stored in S3 at very high speeds. Amazon FSx for NetApp ONTAP brings enterprise-grade NetApp capabilities into AWS. It supports advanced data management features like snapshots, cloning, replication, and storage efficiency tools. This is commonly used by organizations already familiar with NetApp technologies that want the same operational model in the cloud. Amazon FSx for OpenZFS provides a flexible, high-performance file system with strong data integrity features, snapshots, and cloning. It's well-suited for general-purpose file storage workloads that require fine-grained control and advanced file system capabilities. To summarize for the exam, choose file storage when applications need shared access to files, directory structures, and traditional file system behavior. If the workload is Linux-based and needs simple, elastic shared storage, Amazon EFS is usually the right choice. If the workload requires Windows compatibility, high-performance computing, or enterprise file system features, then one of the Amazon FSx options is the correct answer. A final exam tip: if a question mentions shared file systems, multiple EC2 instances accessing the same files, NFS or SMB, or enterprise file system compatibility, think Amazon EFS or Amazon FSx, not S3 and not EBS. When we talk about cached file systems in AWS, we are really talking about hybrid storage, solutions that bridge on-premises environments with the AWS cloud while still delivering fast, local performance. This concept is important for the cloud practitioner exam because it solves a very specific problem: how to keep data in AWS while allowing on-premises applications to access it quickly as if it were local. In AWS, the primary service that provides cached file system functionality is AWS Storage Gateway, specifically File Gateway. AWS Storage Gateway is a hybrid cloud storage service designed to connect on-premises environments with AWS storage services. In File Gateway mode, it presents a standard file system interface, either NFS for Linux or SMB for Windows, so existing applications can continue working without modification. At the heart of this solution is the Gateway appliance. This appliance can be deployed as a virtual machine on VMware, Hyper-V, or KVM, or as a physical appliance. The gateway sits inside the on-premises environment and acts as a bridge between local applications and AWS. One of the most important components is the local cache. Frequently accessed files are stored locally on the gateway appliance. When an application requests a file that is already cached, it is served immediately at local network speed, without contacting AWS. This is what delivers the low latency experience. Behind the scenes, Amazon S3 is the authoritative data store. All files are stored durably in S3 as objects. When new files are written or existing files are updated, the gateway uploads those changes to S3 asynchronously. This means applications get fast local writes while AWS ensures durability and long-term storage. If a file is not already cached locally, the gateway automatically retrieves it from Amazon S3, delivers it to the application, and then stores it in the local cache for future access. All of this happens transparently, without user intervention. This architecture enables several important use cases. One common use case is on-premises file shares, where teams need fast access to frequently used files but want to store everything centrally in AWS. Another use case is hybrid cloud access, where both on-premises applications and cloud-based workloads need access to the same dataset. It is also commonly used for data archiving and tiering, where hot data stays cached locally and colder data is stored in lower-cost S3 storage classes using Lifecycle policies. It's important not to confuse cached file systems with cloud-native file systems. Services like Amazon EFS and Amazon FSx do include internal caching mechanisms, but they are designed for workloads running inside AWS. They are not hybrid solutions and do not provide on-premises caching backed by S3. For the exam, remember this key distinction. Cached file systems refer to hybrid solutions that combine local caching with cloud storage. When you see phrases like on-premises, low-latency local access, files stored in S3, or hybrid storage, the correct service is AWS Storage Gateway, File Gateway. That mental shortcut will help you identify the right answer quickly and confidently on exam questions. When we talk about protecting data in AWS, One of the most important services you need to understand is AWS Backup. AWS Backup is a fully managed service designed to simplify, centralize, and automate backups across multiple AWS services. Instead of configuring backup separately for each service, AWS Backup provides a single, consistent way to manage backup policies, retention, and recovery. The main purpose of AWS Backup is to standardize how backups are created, stored, and audited across your AWS environment. In real-world environments, companies often use many services at once: EC2, EBS, RDS, DynamoDB, EFS, and Storage Gateway. Managing backups individually for each service quickly becomes complex and error-prone. AWS Backup solves this by giving you one central place to define backup rules and apply them automatically. At the core of AWS Backup are backup plans. A backup plan defines how often backups are taken, how long they are retained, whether they are moved to colder storage over time, and where they are stored. Once a plan is created, you simply assign resources to it, and AWS Backup takes care of running those backups automatically. This policy-driven approach removes manual effort and reduces the risk of missed backups. Another major benefit of AWS Backup is centralized management. From a single console, you can monitor backup jobs, view recovery points, and restore resources across multiple AWS services. This is especially valuable in large environments with many accounts or regions where visibility and consistency are critical. AWS Backup is also designed with compliance and auditing in mind. Backups are stored in secure backup vaults, and AWS Backup integrates with AWS Audit Manager to help organizations demonstrate compliance with regulatory requirements. One of the most important features here is Backup Vault Lock, which enforces write once, read many, WRM, protection. Once enabled, backups cannot be deleted or modified, even by the root user, during the retention period. This is essential for industries that require immutable backups, such as healthcare, finance, or government. From a disaster recovery perspective, AWS Backup supports cross-region and cross-account backup copies. This means you can automatically replicate backups to another region or another AWS account. If a region becomes unavailable or an account is compromised, your backups remain safe and recoverable elsewhere. In practical use, AWS Backup is commonly used for centralized enterprise backup strategies, disaster recovery planning, and meeting strict compliance requirements. It also simplifies recovery by providing a unified interface to restore individual resources or entire environments without needing to remember which service originally created the backup. For the CLFC02 exam, remember these key points. AWS Backup centralizes backups across multiple AWS services, uses policy-based automation, supports immutable backup vaults for compliance, and enables cross-region and cross-account disaster recovery. If a question mentions centralized backups, compliance-ready retention, immutable storage, or replacing service by service backup management, AWS Backup is almost always the correct answer. Amazon S3 Lifecycle policies are one of the most important cost optimization and data governance features in AWS, especially for object storage. At a high level, lifecycle policies allow you to automatically manage the lifecycle of objects stored in an S3 bucket without manual intervention. Instead of engineers or administrators moving or deleting data by hand, S3 does this for you based on rules you define. The key idea to remember for the exam is that lifecycle policies help you do two things: reduce storage costs over time and enforce retention or deletion requirements for your data. Let's start with cost optimization. Not all data is accessed the same way forever. In many workloads, data is accessed frequently when it's first created, but over time it becomes less important and is rarely touched. Lifecycle transition actions allow you to automatically move objects to cheaper storage classes as they age. For example, you might store new objects in S3 standard for the first 30 days when access is frequent. After that, the lifecycle policy can move those objects to S3 standard infrequent access, which costs less to store but still provides millisecond retrieval. If the data is needed only for long-term retention, you can continue transitioning it to S3 Glacier Flexible Retrieval or even S3 Glacier Deep Archive, dramatically reducing storage costs. Lifecycle policies are also extremely useful for long-term archiving strategies. A common pattern you'll see in exam questions is a multi-stage lifecycle. Data starts in S3 standard, transitions to S3 standard IA after 30 days, moves to S3 Glacier after 90 days, and finally ends up in S3 Glacier Deep Archive after a year. This pattern is almost always a signal that lifecycle policies are the correct solution. Another important use case is when access patterns are unpredictable. In those cases, lifecycle policies can move objects into S3 intelligent tiering. This allows AWS to automatically monitor access patterns and shift objects between frequent and infrequent access tiers without you having to predict usage ahead of time. The second major function of lifecycle policies is data expiration and deletion. Many organizations store data that only needs to exist for a limited period. Examples include temporary logs, test files, intermediate analytics outputs, or incomplete uploads. Lifecycle expiration actions allow you to automatically delete objects after a specified number of days, keeping your storage clean and preventing unnecessary costs. Lifecycle policies are also critical for compliance and retention requirements. If regulations require data to be retained for a fixed period, such as 7 years, a lifecycle rule can ensure the data is kept exactly that long and then automatically deleted. This reduces operational risk and ensures consistency across large datasets. When versioning is enabled on a bucket, lifecycle policies become even more important. Over time, non-current object versions and incomplete multi-part uploads can significantly increase costs. Lifecycle rules can automatically delete old versions after a certain number of days or clean up incomplete uploads, preventing silent cost growth. For the CLF C02 exam, remember these key points. Amazon's 3 lifecycle policies automate cost optimization by transitioning objects to cheaper storage classes as they age. They enforce data governance by deleting objects after defined retention periods. They operate at the bucket level and apply rules based on object age or object tags. If a question mentions reducing S3 costs over time, managing long-term archives, or automatically deleting old data, lifecycle policies are almost always the correct answer. Now let's talk about transitioning objects with Amazon's 3 lifecycle policies, which is one of the most important cost optimization concepts you need to understand for the Cloud Practitioner exam. In real-world systems, data rarely has the same access pattern forever. New data is usually accessed frequently, but over time it becomes less relevant, less frequently accessed, or purely archival. Amazon S3 lifecycle transition actions exist specifically to handle this reality. They allow you to automatically move objects between S3 storage classes as those objects age, without any manual intervention. The key idea is simple: keep hot data in fast storage and move cold data to cheaper storage. Lifecycle rules let AWS do this automatically based on time, so you don't have to manage it object by object. You should use lifecycle transitions whenever access patterns change over time or when long-term retention is required at the lowest possible cost. A very common scenario is infrequently accessed data. For example, files might be accessed heavily during the first 30 days and then rarely after that. In this case, a lifecycle rule can move objects from S3 standard to S3 standard infrequent access after 30 days, reducing storage cost while still keeping millisecond retrieval times. Another common scenario is long-term archiving. Data that no longer needs immediate access can be moved through multiple stages. A typical lifecycle path might move objects from S3, standard to S3, standard IA after 30 days, then to S3, Glacier flexible retrieval after 90 days, and finally to S3, Glacier deep archive after 1 year. Each transition reduces cost while accepting longer retrieval times. If access patterns are unknown or unpredictable, such as in data lakes or analytics environments, S3 intelligent tiering is often the best choice. Instead of defining fixed transitions, AWS monitors access patterns and automatically moves objects between tiers for you without retrieval fees when data becomes active again. Amazon S3 supports a wide range of lifecycle transitions, and it's important to recognize these patterns for the exam. Objects stored in S3 standard can transition to nearly any other class, including standard IA, one-zone IA, intelligent tiering, and all Glacier tiers. Objects already in standard IA can transition further into archival classes. Intelligent tiering itself contains multiple internal tiers, and objects can move from those tiers into Glacier or Deep Archive depending on configuration. As data becomes colder, transitions generally move in one direction, from standard to IA, then to Glacier tiers, and finally to Deep Archive. Once data reaches Deep Archive, it represents the lowest cost, longest-term storage option, and cannot transition back to higher tiers automatically. For the CLF C02 exam, remember these core takeaways. Lifecycle transitions are automatic, they reduce storage costs, and they move objects to cheaper storage classes as they age. If a question mentions aging data, cost optimization, archival storage, or automatic movement between S3 storage classes, lifecycle transition policies are almost always the correct concept. And finally, when access patterns are unknown, S3 intelligent tiering is the safest and smartest choice because AWS handles the transitions for you. Thanks for watching. See you in the next video.